We break passenger trip time concerns into the following areas: the flexibility in the departure time, the time it takes to get to the initial loop and be moving in a vehicle, and the time after getting off the final vehicle at its loop to reach the final destination. If one or more high-speed intercity legs are involved, we are also concerned with the times before departing on the initial high-speed vehicle and after arriving in the final high-speed vehicle, how long it takes to travel between those loops, how consistent these times are. With a few exceptions like hot meal delivery, goods trip times are far less significant than their cost. We deal with goods trips then in the cost discussion, but note that the mechanisms described here are more than adequate to provide the required goods delivery times. LAN and WAN are best thought of as a safe, high-speed, landmass-wide, taxi and automated goods pickup and delivery system. CUT's personal vehicles provide 24/7 on-demand service for trips within their acceptable range, which is typically in the hundreds of kilometers. Outside of that range, an intercity spatially shared mode is used, potentially with personal vehicle initial and/or final legs. CUT's also has temporal-only shared modes, like taxis, that are also available 100% on demand and mostly 24/7, but outside of dense urban cores, it often takes many minutes between trip request and boarding. Further, such services are generally unavailable in rural areas, including small towns and villages, and have the same range limit as personal vehicles. CUT's has spatially shared modes that are also temporally shared. These are called transit systems in urban areas and passenger train, plane, and bus services between cities. Air travel has the additional constraint that it forms a point-to-point network. These are all subject to some schedule, often with infrequent, or no, direct service to some destinations. Those schedules typically vary significantly throughout the day and are mostly completely unavailable in rural areas. In contrast, NET's passenger trips can commence on demand anytime 24/7 to any destination in the world within the NET's network. The time between a passenger trip request and boarding the initial NET's vehicle would be under 1 minute in any size settlement, as illustrated in our earlier land trip example. In rural areas, the land neighborhoods are much larger, but much of the non-urban population lives in small settlements like hamlets, villages, and small towns, through which a WAN route passes. This is illustrated by this map of the rural Mono Township northwest of Toronto. Every indicated settlement would have a WAN route passing through it. Outside of settlements and away from WAN routes, the response would be a little longer, depending on the land vehicle count, which is a cost issue that we cover later. The initial and final legs of a CUT's personal vehicle trip for ambulatory passengers involve short walks to the parking spots, which are the personal vehicle loops. For non-ambulatory passengers, the walk is replaced by a wheelchair leg. When the trip endpoint is a large building, the parking spot can be a substantial distance from a building entrance. CUT's temporally shared modes provide door-to-door service. That is, the taxi loops are mostly building entrances or exits. CUT's transit modes involve long walks or wheelchair legs to a bus stop loop or a loop within some kind of station. The station loops are much more widely spaced than the bus stops. This would also be true of PRTs. For CUT's intercity modes, the vehicle loops are boarding gates or platforms inside stations or airports. Legs involving one or more of the other modes and potentially more walking are required to get to or from the entrances of those buildings. These buildings can be very large, involving various time-consuming actions to get to the vehicle loop. The differences between CUT's and NET's intercity trips are illustrated in this chart for trips within a landmass with distances from 500 to 2,000 kilometers. For all CUT's trips, a significant fraction of the time is spent before the plane is boarded and after debarking at its respective loops. In addition, there is time spent taxiing at each flight's end. NET's trips provide the door-to-door service of CUT's taxis, except that it is available in all areas and at all times. For trip endpoints near a WAN guideway, and thus a WAN loop, passengers may choose to walk rather than use a LAN leg. Consider our LAN example again in the passenger trip time context. The durations of the animation reflect the actual time for the 4 segments of the LAN vehicle trip, given a trip request at any time of day or night. With our assumed parking spot for the LAN vehicle, it takes about 15 seconds from the trip request to the vehicle arriving to pick up the passenger. We assume 5 seconds for the person to board the vehicle. then another 17 seconds to carry the person to the WAN guideway. Upon arrival at the WAN guideway, it will take seconds before the passenger, ambulatory or in their own compatible powered wheelchair, is on their way in a WAN vehicle. As we shall see in the cost discussion, it does not take many LAN or WAN vehicles to provide such response. For all trips within a landmass, once boarded, the WAN vehicle could travel to the destination WAN loop with no need for stopping. A LAN vehicle would be waiting there, if desired, to perform the final trip leg. WAN does provide slightly larger and more comfortable vehicles for long intercity trips. In the event that those are used, there would be vehicle switches before and after entering the high-speed intercity guideway. Those switches would only take seconds to perform. If a NETS air leg is used, there would be at most a 15-minute time between WAN vehicle departure at the airplane loop and flight takeoff. The reasons for that are specified later. We now come to the time spent traveling between the initial and final trip loops. For personal vehicle and taxi legs, the travel time is slow due to safety-motivated speed limits and, inside settlements, frequent stops at 2D intersections or crossings. Typical urban average speeds are in the 20 to 40 km per hour range. The lower end of that range occurs inside large urban cores. In rural areas, the speed limits are higher, and there are far fewer stops, so the averages are in the 80 to 90 km per hour range. These speeds, the top speeds, and frequent stops are all illustrated with this chart of the US EPA's city and highway driving cycles. There can also be substantial travel time delays from rush hour congestion or temporary lane outages due to construction or accidents. Surface-level transit vehicles have those same constraints, but have added delays related to their spatial sharing. There are far more stops to pick up and drop off passengers. The trip length is increased because their routes are designed for the shared demand rather than the needs of a single traveler's trip. When the initial and final loops do not lie on the same route, transfers are required. That introduces further delays. For the same pair of trip endpoints, these modes have average speeds in the 10 to 30 km per hour range. Intercity modes, as noted in the chart, have trip times dominated by the time not spent traveling in the high-speed intercity vehicle. As with transit vehicles, both the distance traveled and the transfers can add a lot of time for multi-leg trips. Note that the effective speed for the 500 and 2,000 km single-flight trips, even with planes traveling at 900 km per hour, are about 150 and 350 km per hour, respectively. LAN legs, if used, would only take more than 1 minute for rural locations multiple kilometers from a WAN guideway. Once a WAN vehicle is boarded, it travels to its destination without stopping and with no safety-motivated speed constraint. Capacities and the density of the high-speed network are such that those times will be consistent to within a couple of minutes at all times. As we shall see, WAN uses staged speeds across multiple tracks to have the highest speed track on non-intercity and expressway routes, having speeds of 180 km per hour at the busiest times, and potentially a little higher at other times. These are what most CUTS road vehicles could achieve if they were not constrained by the speed limits and frequent intersections. On intercity routes, the top speed track would support speeds in the 450 km per hour range. As we shall see, this is achieved by using even more tracks with staged speeds, dynamic trains assembled using the vehicle module dynamic coupling mechanism, and by exploiting the light, fully loaded mass of WAN vehicles in a number of ways. Many current CUTS high-speed rail systems have cruising speeds of 350 km per hour, with experimental runs exceeding 500 km. This is enabled by having off-grade, tracked guideways with only 3D crossings, but the large mass of the vehicles makes such things expensive. Further, the straightness of the guideways required to provide appropriate passenger comfort at these speeds often leads to problems with obtaining the rights-of-ways needed to build these region-dividing guideways. A number of production cars also exist with top speeds approaching 500 km per hour. The issue with top vehicle speed is not whether we can produce vehicles that go fast. Rather, there are few conditions where those speeds can be used, and even when they exist, there may be the same comfort issue as the high-speed trains. Also, the large mass and size of even these vehicles is such that these all have motors producing 1,000 kilowatts or more, that also fit in the necessarily small, sleek sports cars. These supercars are very expensive, WAN uses multiple tracks with staged speeds to support high top speeds and high vehicle throughput capacities. Due to the small capacity of each vehicle, WAN needs multiple tracks with short headways to provide sufficient overall cargo throughput capacity. But that means at some point slower traffic on one track must switch into a higher speed track. Such switching is illustrated in this drawing. On CUTS expressways, the biggest speed difference occurs at the entrance ramps. These are very long to allow a slow entering vehicle to accelerate to a speed sufficient to enter a gap between vehicles in the outermost expressway lane. The speeds on those lanes are typically in the 100 to 120 km per hour range. There are additional lanes with increasing speeds toward the innermost lane, but the speed differences are small, and the top speed lanes seldom support speeds more than 160 km per hour. Even that is not available in busy periods due to the small headway in each lane. But WAN should be able, at least for intercity trips, to have top speeds at least what the supercars are capable of. The problem is that the gap between vehicles and the track being switched into must be large enough for the switching vehicle, S, to match the speed of the trailing vehicle, T, before T overtakes S. But T is closing the gap with S at a rate that grows as the square of the difference in their speeds. Assume S is on a track at 100 km per hour, like an expressway. T is moving at 250 km per hour. If F switches track just after L passes, and S accelerates at 1 meter per second, the gap between L and T would have to be over 800 meters. But we want speeds above 450 km per hour. This is how we do that. WAN intercity routes consist of two guideway types, which we call expressway and intercity guideways. Their track structures are indicated here. With some big exceptions, the WAN expressway guideways run in opposite directions on either side of CUTS expressways. One bidirectional WAN intercity guideway runs between the WAN expressway guideways along the CUTS expressway median. The main exceptions are for undeveloped areas where no expressway exists, and to address the passenger comfort issue with vertical direction changes on hills or valleys and lateral changes on curves. We will discuss this soon. The 5 numbers given for each track reflect the nominal speed in kilometers per hour, the minimum vehicle headways in meters, the cruising energy consumption rate in kilojoules per kilometer, the input power required for cruising in kilowatts, and finally the power required to accelerate a fully loaded WAN intercity vehicle at 1 meter per second at the track speed. We will discuss the energy numbers soon. WAN intercity routes use a staged speed difference between neighboring tracks of 10 meters per second or 36 kilometers per hour. There are 7 stage switches from the 180 km per hour track on the expressway guideway to the 468 km per hour track on the intercity guideway. From the point an S starts accelerating, even at 1 meter per second, to when it matches a T's speed, T will have made up just 50 meters, which is far less than the specified headways per track. We will discuss the reason for the specified headways soon. A long entrance track, like expressway entrance ramps, is used to reach the 180 km per hour track. This is similar to the CUTS expressway entry ramps. As with the CUTS expressways, such ramps occur only where WAN arterial guideways cross the intercity routes. There are also long switching tracks between the fastest expressway track and the slowest intercity track. This supports a difference of 20 meters per second or 72 kilometers per hour between those tracks. Note that even higher speeds could be possible by just adding more tracks, but that would exacerbate both the comfort and energy issues, as well as introduce potential problems with wheeled vehicles. We will discuss each of these topics soon. WAN requires a switching mechanism that can perform well at these high speeds. The mechanism should not use any mechanical elements in the track and should be under control of the individual vehicle. There are many options for such a mechanism. The current WAN switching mechanism is based on high-strength permanent magnets embedded in the track at switch entries and strong switching magnets on the vehicle bogies. The low mass of the WAN vehicle ensures that this can perform even at these speeds. For the intercity guideways, the switching tracks are widely spaced and extremely shallow, limiting both the force required and the acceleration and jerk felt by passengers at switch entry. Each WAN bogie also has 8 wheels as indicated here, which ensures that at most one wheel is ever passing over the track slot during a switch. The stage speeds, and thus acceleration mechanism, both exploits and contributes to the low mass of WAN vehicles. WAN vehicles may be thought of as CUTS freight trains with distinct engines or propulsion modules, and freight cars or just car modules. Each car module uses two bogies, one at each end. The propulsion modules use one bogie, with larger motors or batteries being carried at the bottom of the load pole outside the track. The modules dynamically couple, using the electromechanical couples at both ends of each bogie. Such high-speed coupling has existed at least since the 1960s space races. It is greatly simplified by having both modules moving on a track. The number of power modules dynamically attached to each car satisfy the upcoming demands for cruising and acceleration power. This multiple track mechanism is also the main reason that the top speed track on inside settlement or IS arterial routes would have its vehicles moving at 180 km per hour during peak periods. During off-peak periods, the speed on that track could be high. With the exception of dense urban cores, there is one such guideway running in opposite directions on either side of CUTS arterial streets. Core streets may have only one per street, with the directions alternating from street to street that are often just a couple hundred meters apart. As shown here, these guideways have loop tracks, which allow vehicles to stop to pick up or drop off their cargo. The intercity routes have no loop track, and all loading and unloading occurs on WAN arterial track loops before entering the long expressway guideway entry track. The horizontal spacing between tracks on IS arterials cannot be as wide as on the intercity guideways due to the near proximity of buildings. That and the passenger comfort needed for longer trips are the primary reasons the intercity vehicles are slightly wider than the non-intercity ones. The loop track would be just over 2 meters from the street edge. The area below must be clear for the bottom of the vehicles to descend to. WAN vehicles always confirm that space is clear before descending. Note that as a vehicle can stop anywhere on a loop track, and there are switching tracks onto and off the loop track every 50 meters, on average the space between loops would be about 20 meters. That is why our LAN example trip just needed to reach the WAN guideway to have access to a WAN loop. There are a similar pair of switching tracks at a 50-meter spacing between every other track pair. That means that although a vehicle must perform 3 switches to get from the loop track to the top speed track, the main constraint on how quickly that can occur is the accelerations, and thus acceleration power it uses. The speed difference between the loop track and the next is 72 km per hour. That is possible because at these low speeds, little power is required to accelerate even at 3 meters per second, which is still comfortable for these short periods. Reducing the speed difference to 36 km per hour can be done within 16 meters before entering the switching track. With an exception described soon, the second track is used as a moving track primarily for vehicles carrying goods. For those carrying passengers, it is a short stage to get to the higher speed tracks. The 72 km per hour difference between the second and third track is available partially for similar reasons, and because the intervening switching track provides an acceleration span in which the vehicle is not on either other track. Returning to Toronto, the trip for our LAN example load point to the Rogers Centre to watch a baseball game would spend most of its time on the top speed Yonge Street track. The entire 18-kilometer trip would take under 7 minutes at all times. In contrast, the car trip would take about 26 minutes in the middle of the night and often 55 minutes during the day. Subway trips would also be about 55 minutes while running, but during the night, transit trips would be closer to 70 minutes. The reason for the WAN trip time consistency is the high capacity of these individual routes and the density of the network of these high-speed, high-capacity routes. The final version of this multi-track switching model occurs with the OS arterial routes that mostly run along CUTS rural arterial roads outside settlements. These are bidirectional guideways running on one side of such roads. They share a common loop track that runs between the guideway support poles. The presence of this track means cargo can be loaded at any point along such guideways. The speed differences on these guideways are even larger than the IS arterials. This is possible as the traffic density on these routes is quite low, so the headways between vehicles are large enough to accommodate the required acceleration. Also, as with the IS arterials, individual goods carrying vehicles move on the lower speed track. With OS arterials, every route on this regional map of the Toronto area provides loops roughly every 20 meters, and an ability for passengers to be traveling at 180 km per hour or sometimes faster, to their destination. From even the furthest points on this map, a trip to downtown Toronto would only take about 20 minutes at all times. The final type of WAN route are collectors. Collectors run mostly along cuts, urban and rural minor arterial and collector roads. Collectors have one bidirectional 3-track guideway with a loop track running between the support towers. Collectors are largely used just to reduce the size of land neighborhoods if only arterials were used. Collectors do not need significant throughput capacity or speed, as vehicles spend only short periods on them before entering an arterial route. The lighter blue paths forming the west and north boundaries of the Young Finch neighborhood are examples of collectors in urban areas. In the Mono Township, collectors would be used for WAN routes within the township interior, with arterials along the boundaries. Note that the speed difference between the loop track and the traffic stream moves at 108 km per hour, or 30 meters per second. This is viable due to the low traffic demand on the moving tracks and the ability to have rapid initial accelerations where the power requirements are low. There will seldom be a long period before a gap between vehicles is wide enough to allow a vehicle to enter from a loop. The issue with lateral or vertical changes of direction is the accelerations felt. The acceleration felt grows as the square of the speed divided by the radius of the direction change. Comfortable regular acceleration should be under 2 meters per second. At 100 meters per second, or 360 kilometers per hour, that means the radius must be greater than 5,000 meters. At 500 kilometers per hour, that has grown to over 9,600 meters. In developed areas, the WAN intercity routes would mostly run along existing cuts expressway rights of way. But where there are no such expressways, or where the lateral or vertical direction changes of the expressway right of way would constrain the speed, the WAN intercity routes would need to cross areas outside the expressway right of way to straighten or flatten the guideways sufficiently to remove the speed constraint. The WAN guideway design is a cable-stay bridge-style structure, mostly with small support towers on a roughly 50-meter spacing, supporting 3 to 9 light beam tracks. Individual tracks with the corresponding lateral supports, covers, and cables have a mass under 10 kilograms per meter of track length. There are also guy wires providing a degree of lateral support to offset bending moments from wind or vehicle loads. The lightness of this structure is enabled by a fully loaded WAN intercity vehicle mass under 400 kilograms. Much taller towers, where needed, can support much longer spans to allow the required flatness and straightness for a desired speed given almost any terrain. There are a number of options where very long spans are needed. However, the very light, static, and dynamic loads allows even long spans to have low costs. Because of the huge vehicle mass, flattening by using significantly varying viaduct support heights is not a realistic option for high-speed train viaducts. In very rare instances, in rural areas, an expensive tunnel may be required. This is the main option for high-speed rail, which contributes to the high average cost per guideway kilometer. In passing through large urban areas, a tunnel may be required if we want to maintain a high top speed. Note that WAN has no stations requiring a stop. The WAN guideways do not block ground traffic, except at the small towers and guy-wire anchor points. As described later, they would have minimal disruption during construction. These characteristics largely eliminate the right-of-way acquisition issues needed to provide adequate flattening or straightening. Those, along with the corresponding high guideway unit costs, are the main constraints on high-speed rail deployments. The cruising power and energy consumption rates become a cost issue at the higher speeds. We deal with that in detail in the cost discussion. But to summarize, the basic mechanism involves minimizing those rates as much as possible for all speeds and by using dynamic trains on each track, with minimum lengths that increase with the track speed. The light, fully loaded mass means at all speeds the energy factors are dominated by air drag. The small frontal area allowed by the restriction to 2 passengers riding in a tandem configuration and an optimized aerodynamic design minimize the air drag at all speeds. The cruising energy and power requirements for single WAN vehicles on each track were given in the guideway drawings. These assume a 10% loss during battery charging and a conversion efficiency from electrical to propulsion power of 85%. Those are typical of CUTS EVs. WAN assembles dynamic trains using the same dynamic coupling mechanism used to combine its modules. Anytime a vehicle or train switches track, it can couple with the vehicle or train it enters in front of. This is just a matter of speed matching. Trains easily split and rejoin to allow vehicles to easily depart as they approach their exit. For trains, the air drag cruising power and energy consumption rates required per vehicle are reduced by the number of vehicles in the train, but increased by a small linear growth in some air drag factors. The key factors affecting the WAN train drag factor growth are the skin friction, which is proportional to the surface area, and the smoothness of the joint between vehicles. The final WAN vehicle design would optimize both these effects. The result of this is that even at 468 km per hour, per vehicle cruising power and energy consumption rates for a train of 25 vehicles would be under 10 kilowatts and 50 kilojoules per kilometer, respectively. WAN could ensure those are maximum values for all tracks by putting minimums on the train length on each track. 25 vehicles, which would be 150 meters, is not a long train. If all of those were carrying goods, they would have a cargo less than one-third that of a single fully loaded semi-truck. This implies a large number of vehicles, but we cover that potential issue in the cost discussion. Those numbers are well within the range of commodity motors and battery packs. At those levels, we can see this is really just a cost issue. As a reference, the most efficient EVs today consume about 700 kilojoules per kilometer in highway driving, while internal combustion vehicles are in the 3,000 range for cars and higher for small trucks. More on this in the cost discussion. The main issue with power requirements is then related to the acceleration used at track switches. There is no train benefit here, as that power is the product of the vehicle mass, speed, and acceleration. The low mass relative to CUTS vehicles is a big benefit here. WAN decreases the acceleration used as the speed increases, but the acceleration power still often exceeds the cruising power, particularly at the lower speeds. Further, the greater the power, the more massive the motor, which in turn requires more power. The WAN solution to this is the modular vehicle design noted earlier. WAN propulsion modules can be dynamically added or removed from the vehicle set. So WAN just adds an appropriate set of propulsion modules to satisfy the coming acceleration demand prior to a switch, then decouples any not needed to satisfy the coming needs for cruising or further accelerations. As accelerations are of short duration, the same power modules can be used for multiple accelerations. Further, during cruising, the motor mass required for acceleration is not a factor in the cruising energy requirements. WAN vehicles also provide an energy module to provide unlimited range. The base batteries in a propulsion module could be similar to the 1 megajoule battery pack on some e-bikes. Two of these would provide a range of 40 kilometers at 50 kilojoules per kilometer. The energy module would have much larger batteries. These would be wirelessly recharged near guideway support towers. As needed, an energy module would couple with a propulsion module to be carried to a vehicle where it would couple and then recharge the propulsion and car module batteries. As our chart shows, WAN provides shorter door-to-door trip times than CUTS air travel for even single-leg flights up to at least 2,000 kilometers. Where multiple legs are required, the advantage is even greater and extends to much longer trips. For trips longer than 2,000 kilometers, LAN and WAN may also be preferred over CUTS intercity trips within a landmass. For example, for a trip from New York to LA, travelers may choose to stop in Chicago, St. Louis, or any other city on their route. They could have a nice restaurant meal there, potentially take in a show or sporting event, or do a night on the town. Whenever these activities finish, they continue their trip. Departures on either leg can occur 24/7 with no change in the leg time or cost, which would be $0. The flexibility of such options would decrease the motivation for long single legs like the corresponding direct CUTS flight. There could also be a much higher speed backbone version of WAN. Up to whatever limit exists for wheeled operations, it could just add more staged speed tracks, requiring even longer trains, to the basic intercity guideway mechanism. While higher speed train systems have considered using maglev rather than wheels, we can show that this is largely a result of the high mass of the trains. With intercity WAN vehicles, the per-wheel load is about 200 newtons, or less than 1% of CUT's high-speed trains. This should allow WAN vehicles to operate up to 900 km per hour if sufficient stages and train lengths are viable. In the US, one such 3,600 km WAN backbone would run mostly along I-80 from roughly Binghamton, New York to Salt Lake City. Between all points in the Northeast and any city on the West Coast, trip times would be similar to single-leg CUT's flights. Any straightening or flattening of the intercity routes would be made to accommodate such speeds so that in the event such a backbone addition was made, appropriate routes would already have been built. Until such a backbone is built, nets would use some planes for the longest trips within a landmass, but those planes would operate out of the small number of rural nets airports designed primarily for trips between landmasses. WAN would provide a 450 km per hour or faster feeder network. The catchment area and corresponding population served for each airport would be much larger than the single large city CUT's catchments. For example, an airport near Binghamton, New York would be within a 1-hour WAN trip for over 70 million people. A small number of airports servicing large areas could then have frequent departures to a small number of directly connected airports. With airports in remote rural areas, noise concerns are mitigated, meaning 24/7 service is viable. Given that most trips between landmasses span multiple time zones, being able to service arrivals or departures at all hours may be useful. WAN vehicles would provide loops at the equivalent of CUT's plane boarding gates, eliminating much of the CUT's terminal times and costs. It would not be unrealistic for passengers to be in the air to most destinations within 10 to 15 minutes of arrival. When higher-speed airplanes become available, the smaller number of airports would allow their much more rapid, effective deployment than possible with the one airport per city CUT's model. In summary, WAN, with LAN as the last-mile system, would provide trip times that are always less than the best possible CUT's trip times. The only technologies required that are not in widespread deployment today are the high-speed switching and dynamic coupling mechanisms. However, versions of both have existed for decades, just not in the precise way they are used here. There is no significant technical risk. What does exist can be mitigated quickly by demonstrating working versions of these mechanisms. The outstanding questions regarding nets then concern its cost. As we will show next, this would be a one-time capital cost, mostly to build the WAN guideways and energy infrastructure. Together, for the US, these would be on the order of 2 years of government expenditures on CUTs. That would allow all LAN and WAN use to be free for both passengers and goods.